And before we go to the general transformation or general coordinate system, there's one more topic in the Cartesian coordinate. It's called pseudotensor. So all this transformation, we are discussing those in rotation. So you have x, y, z coordinate. You just rotate it, just according to the usual sense of rotation, keep rotating it. And you can check that all these transformation matrix with rotation, the determinants of this transformation matrix, whatever we describe that this quantity, or which is equivalent to what we described at first EI prime dot EJ, this kind of transformation matrix. It's just basically the same. You express that in coordinate system. And we already said that, say, whatever you call, give it a name, so it's like J, right? And I think that, yeah, using S. I forgot the notation. But if for Cartesian coordinate, this transformation matrix, the determinant is 1, because we already showed that the inverse of S, so S inverse, is equals to S transpose. Right. That's what we at first discussed about this transformation matrix. And then you obviously then S inverse is Kronecker delta, or using matrix, this is identity matrix. And then the determinants of S multiply the determinant of S transpose. This is just transpose. Inverse is just transpose for this Cartesian transformation. And the determinant of S transpose is the same as determinant of S. Determinant is unchanged when we do the transpose. And the determinant identity matrix is 1. So the determinant square is 1 for rotation. Okay, so for rotation, you can also check that quite easily that the determinant is not just square is 1, the determinant is 1. It's just if you stay with rotation, that is quite easily checked by writing it out explicitly, like all this rotation that you can write. That in chapter 3, there are some examples of that. But if you have generalized this rotation to what we call the improper rotation, so you have x, y, z. So if you reverse the one of the axes to is negative, so it's basically change x to minus x. Change the x-axis to the minus x direction. This is your new x prime. This is x prime is going the other way. Then obviously the determinant will change sign. Change to negative. So it's like it's because you cannot rotate that just by usual rotation you get to that one. So what we call we have the handiness. So one is the whatever you call it, the right hand coordinate system. You cannot change that to a left hand coordinate system. So you need to reverse the direction of one of the coordinate, right? One of the Cartesian coordinates. And if you reverse 2, then the determinant becomes 1 again. Right? That this left hand becomes right hand, becomes left hand again. And then, but if you reverse all 3, then the determinant becomes -1 again. Right? And that if you reverse all 3, it's just the same as what we call spatial inversion. So whatever you have the spatial vector x. In a new coordinate system, this we call x prime would be negative x. Right? You read this reverse all the spatial all the direction of the coordinate vector, that becomes a whatever we call the x becomes negative x. Right? So that is spatial inversion, and all those are fine, except there's some quantity that are involved in physics. They don't transform just like what we call here the according. If you generalize this, translate this linear transformation matrix, including the improper rotation or this spatial inversion or refraction. So you refract just one of the coordinate, that is a refraction. So, so if you have a vector, it's not transformed just like that for a general linear transformation, but also involve a determinant of A. In determinant, what we call S. If you multiply with determinant S. That is what we call a pseudo vector. Right? So this the ordinary the discussion so far we define a vector according to this one, right? According to this one, and but if the transformation is not just this one, this basically we're saying we are staying with just proper rotation. A proper rotation, the determinant is always one. So this will valid for either. If you stay with just proper rotation, this is valid for vector and pseudo vector. But if you include a generalized coordinate transformation, including improper rotation or refraction or spatial inversion, then the determinant of this transformation matrix, or what we call S here, and that will be that it can be -1. It can, because the square is 1, it can be either 1 or -1. So, but if it transform by this one multiplied by the determinants of the transformation matrix, that is called a pseudo vector. Okay, so that is how you define that. Okay, and we have more example of these pseudo vector, and we can generalize that to pseudo. This is pseudo vector, but you can generalize to pseudo scalar. So basically, if you do a refraction, then the quantity of a scalar is, instead of unchanged, it changes the negative sign. That is a pseudo scalar, and then we can have a pseudo tensor. So basically, the same transformation measure as a tensor, but you multiply by the determinant of S. That becomes a pseudo tensor. Okay. It's just that you can express physical law obviously with tensor, and you can also express it with combination of tensor and pseudo tensor. But what you want is to keep the transformation the same for all terms. You write down equations, all the transformation for each term in the equation should be the same. If they are vector, they should be the same. This is vector for all terms. If it is pseudo vector, they should be pseudo vector for all terms. If you mix that the term, then if you do a transformation, one will change sign, the other will not change sign. Then the equation change. That is not good, right? That is involving the what we call what we assume to be the physical law that should be unchanged, the parity. So this is what we call parity conservation. We think we assume that all the physical, if there's a mirror and you look at whatever happened in the mirror should be described by the same physical law as in the real physical space. And at least that's what our assumption. Although later there's some subtleties, so you just it depends on how you keep other quantity unchanged or transform or not transform. The, uh, the discovery that the weak interaction just break the parity is not the same. The mirror world, if you change just look at the weak interaction in the real world and the world in the mirror, the parity, they are not the same. And but that's just kind of violating the assumption of that later on you can fix that by you, you, you just haven't taken into account that we go to the mirror world, there are some other things actually change. So so it changed not just by changing all this coordinate system, but also by changing the charge to in the charge also. So basically, if you have electron and the mirror world becomes anti-electron or the positron, that kind of thing. Then you combine them, then the conservation seems to be restored. So this is that the parity violations of this P violation, but if you combine charge conjugate, then CP seems to be valid. And until we will discover CP is also not valid in some interaction, some nuclear interaction. And so finally, what is valid is you combine C and P, the changing the charge, and then the parity combined with time. You need to reverse that also. That becomes valid again. So CPT that isn't breaking down. So do a transformation, you go to the Mueller's law, you need to change this charge and then change the time direction. Then this is valid. It's conserved. Well, it's just looking at this the parity change, how you some quantity change some. Right. So now the example, obviously a pseudo vector of obviously you probably learned that in undergraduate ENM. Like the magnetic field is a pseudo vector instead of a vector. But in that is staying with the old undergraduate level of ENM. When we learned about more incorporating the special relativity, we know the electric field and magnetic field, they actually combine and form a second rank tensor. So it just depends on how you look at it. If you look at magnetic field as a vector, you can see it's a pseudo vector. Another pseudo vector is like if you have a vector, if A is a vector, then you take what we call the corresponding, that becomes a pseudo vector. And you can check that, check this quite easily. But all these also involve one particular pseudo tensor. This is the third rank, or we call that the Levi Civita symbol. And say if you have a equation like that, B equals curl A, and we usually it's and going back to undergraduate level notation, the components say D, the I component of this relationship is just the Levi Civita symbol, the epsilon I, jk, and then partial xj. That in undergraduate level, this is a subscript, and then ak, and also sum over j in Einstein notation. Right? That's just how you define the cross product, and this Levi Civita symbol. We probably learned that before. You can It's also called the totally anti-symmetric tensor. Obviously, it's normalized in the sense that if you interchange any of these, or if two of these indices is the same, then they will be zero, zero, zero if I equals to j or etc. Any two indices the same, they are zero. And this is a property of anti-symmetric. Anti-symmetric means if you interchange the two indices, any two indices, then it obtains a negative sign. So that therefore, if you have epsilon 1, 1, 1, 2, something like that, it must, because you interchange the indices, it gives you the negative sign. So that equals epsilon. If you interchange the first two, it's still 1, 1, 2, right? But you get a negative. And the only way to satisfy this equation is that they must be zero. Okay, so that therefore is the property of the anti-symmetry, right? And then it's normalized in the sense that when they are not the same, obviously there's a one. You just assume as a certain order is one. If I j k equals to 1, 2, 3, right? And minus one if you obtain ijk from odd polynomial, odd number of exchanges. It's kind of difficult to say exchanging from 1, 2, 3. Like, say if you have 2, 1, 3, you obtain 2, 1, 3 from 1, 2, 3 by one exchange, right? You exchange 1 and 2, you get 2, 1, 3, right? Then that component is minus 1.
So it's
yeah, no problem.
ijk. So if you change, let's say ik, but what follows next does not affect the sign. Let's say, for example,
well, you keep doing this. If 2, 1, 3 is minus 1, then 2, 3, 1 will be 1 again, because you obtain this by two permutations, two exchanges. Exchange 1 and 2, and then 2 and 3, you get this one, right? That's 2. That's number of 2, right? It's that even number of exchanges. If it's odd, 1, 2, 3. So this is 1, 2, 3, and even number of 1, 1, 2, 3, and if you can obtain it, if you exchange it 2 times, then it go back to 1. Is that okay? And that is also a property of the anti-symmetry, because that obviously just the anti-symmetry means you exchange the elements, the two indices, that you get a negative sign. Obviously, this epsilon 1, 2, 3, and 2, 1, 3, they are the same. I mean, by exchanging 1 and 2, right? So the anti-symmetric property requires that they should be negative of each other. So if you choose this to be 1, the other must be minus 1. Okay, so that's so therefore this is called a totally anti-symmetric tensor. Okay, and this is third rank, but for arbitrary number of dimensional space, you can increase generalize this to any number of indices. Your 4 dimension is IJKL, right, and so on. And like, whatever number of dimension, you can define this Levi Civita symbol according to the same rule. Okay, and now the idea is to show that this is a tensor, and actually not a tensor, a pseudotensor. Okay, and that may need a little patience to see that. I mean, the textbook has 2 lines to show that, but I don't know whether it's easier for you to understand. But we'll try. Okay. Okay. So let's get some space here. This is the definition. Stay with just that rank, just basically three-dimensional space, but the idea you can generalize to any dimension. And the idea is you assume that at one coordinate system you have this epsilon. You define epsilon at one coordinate system, and then you do a generalized transformation, including the improper rotation, and then you define an object using the pseudo-tensor rules, like in the equation 4.29. So you transform to a new system, prime coordinate system with A to ijk, transform by this except that the text now using A instead of S. Remember previously we defined the transformation matrix as now in this example you use A. It doesn't matter whether you call it whatever variable you define your transformation matrix, doesn't matter. So A is now your transformation matrix, and the components of the transformation matrix is this the A. The A is A, ij is whatever. No, it's in this sense it's not separating in the subscript or superscript. It's this little aij. Right. This matrix has element, what we call this little aij. Okay. So this is a transformation matrix. If you transform it according to the pseudo-tensor transformation, it should be it equals to this A I P A J P Q R A K P Q R I J K P Q R, and then the epsilon P Q R. Okay, so without that, it says a transformation of Van Tensor according to these are the transformation matrix, right? But then adding that supposedly is pseudo tensor transformation. Now you want to determine what this thing is in this new coordinate system. That actually is the prime coordinate. This is in the non-prime coordinate, and you wanted to see what that is, right? All right, and now the following step might need a little bit patient, right? Because the first you just consider all these cases, right? If you have two repeated index, ijk has this repeated index I equals j or j equals k or whatever, all these cases. Like consider I equals j, you have two of them are the same, so a to I k, right? Right, explicitly I k. So the determinant of a, so you have a I e, a I q, and a epsilon p q r, right? But because the order they have the same thing, we can interchange the order p and q, right? And call this p and call this q, right? So you call this p and call this q. Doesn't matter. It's just change the position, right? And then it's just the same as calling p and q. So p and q. Instead q and p and q, you can q and p. It must equal to that. So this equals to that. But you know that this one is equals to the negative of this one. So it's equals to the negative of the same thing, right? So it must be zero. Okay, so you have two repeated index according to this line, then obviously you have two repeated index. This equation will make sure that it must be zero. It's okay because you have this epsilon over here. right? So we satisfy the first one, right? Now, if you have this ijk equals 1, 2, 3, right? We just stay with that. So a 1, 2, 3 will be determined of a multiplied by a 1 p a 2 q. All these are sum over. Because I mean this is implicit because of Einstein notation p and q and r. Your textbook actually put the summation explicitly, but you understand this is sum already. Okay, so CQ, 3R, epsilon, CQR. All right, and now that require you to remember your definition of determinant. If you remember how you calculate or you define determinant, this is this object, this product, other than this determinant A, as the determinant of this matrix A. This part is a determinant, right? Do you see that? Not sure. Anyone not seeing that? Have you seen that? This is your definition of determinant. Not some of you are not. Should be an equation in chapter 2 that we skipped. I said I suppose you learned some of these things before. Should be very early to define determinant. Let's see. Yeah, this is equation 210. This is equals to determinant. Okay. That's just one way to define a determinant. And the reason is that whatever remember how you calculate determinant. In this case, the transformation matrix is just a 3 by 3 square matrix. So that is easy to see. So you have A11, A12, A1C, A21, A22, A23, A31, A32, A33. Right? You know the determinant is this times this times this is positive, this times this times this is positive, this times this is positive, and the other way around, this time this is negative, this time this is negative, this time this is negative, right? That's how you calculate determinant, right? And now you realize the rule has this property that all these terms involve one element in one row and one element in one column. You don't have two elements from the same column or elements from the same row. It means that it's satisfied that this you have repeated column or repeated so 1, 2, 3, or make sure that the column are different. One is from column 1, the other from column 2, then it's from column 3, right? Column 1 is I should add 1. This is 1. This is row. The first row is row, right? This is also first row. This is second row. This is third row, right? But then you cannot have elements from the same column. Then P and Q. If from the same column, then the epsilon will kill you. Right? This epsilon will be 0 if you have repeated index. So basically, you exclude all the terms that with the same column, right? And then by how we calculate the positive and negative, you know that is the same rule as here. Say this time, the column is 1, 2, 3, right? Meaning PQR is 1, 2, 3, that's positive, right? But you exchange the two, instead of 1, 2, 3, 1, 1, right? This is 1, 2, 3, instead of 1, 3, 2, right? You have 1, 3, 2, then that is negative, right? So that is following the same rule. Right? If you include all the terms, sum over all the terms, this will give you exactly what we usually call determinant, right? How you calculate determinant. So that is a determinant. So this means that this 1, 2, 3 element is determinant A squared. This is one. All right. Then now the rest is just according to this rule. If you interchange this instead of 1, 2, 3, interchange by one odd order, say 1, 3, 2. Then this becomes 1, this becomes 3, this becomes 2. And obviously, you can restore the same by interchange Q and R. Interchange this 2 terms, become 1, 2, 3 again. You interchange this to restore it the same. You also need to interchange Q and R. You interchange Q and R, they introduce a negative sign. So this means 1, 3, 2 will be negative of 1, 2, 3. So that will give you a negative determine negative 1. But this one is 1. You interchange 1 will give you a negative 1 by this consideration. All right. So then you can the same logic is that if you interchange 2 times, you reverse it again, then it becomes 1 again. So it all satisfies this. So it means that all this consideration means that this one is proportional to epsilon ijk, and the proportionality is 1 because whenever it is 1, 2, 3 is 1. Right? So aj, which is epsilon. Okay. So it means this is, remember, this is after you transform it, and this is in the new coordinate system, what we call the pine coordinate. In the pine coordinate, this tensor take the same value as this symbol, as this definition, even in the new coordinate system. And it transforms from the old coordinate system according to this rule. So therefore, this object is a pseudotensor. Pseudo in 2-dimensional space is a pseudo third rank tensor. Okay. Yeah, it take a little bit of thinking to from this rule to say that this equation implies this a to ijk is epsilon. It's okay, is it? You're confused about this? Can you follow all this? This how we define. We think if we transform from the epsilon ijk in the new coordinate system, this is in the x coordinate system. This is the x prime coordinate system. Just a number that we define by this equation. No, it's after all this consideration, we show that eta ijk is just epsilon ijk as defined in here. So it's exactly this one. Because by this consideration, we checked it satisfies all these lines. Right? If you have 2 repeated indices, this will automatically be 0 by this equation. This is before I have this adding this line. Before I add all the eta 1, 2, 3 is determinant A multiplied by this one, and according to 210, equation 210 of the textbook, this object is determinant A. So this one is determinant A times determinant A is determinant A squared, which is 1. And because we already showed that the determinant of square of this transformation matrix is 1, because of the properties A inverse is A transpose. Is that okay? It combine everything, combine all the consideration that show that this object defined like that is just the same as this epsilon ijk as defined in here. First, we define this object, which is just a symbol, just a notation to calculate this object, which has 3 indices, and it satisfies all these rules. So for all these different cases, it take different value. Okay, and so this is well defined. And we want to transform this object from one coordinate system to another coordinate system according to the rule of transformation of a pseudotensor. And we show that according to this rule in the new coordinate system, this object is exactly the same, epsilon ijk. And so that the epsilon ijk transform in this one is the pseudotensor transformed by the rule of how we transform a pseudotensor. That is the logic. Okay. It's a little abstract, but it's essential. Even if it's a little bit difficult to guess, because many physical law will involve this epsilon ijk. In many cases, we write physical law involving it, like a curl product, like the magnetic field. We define this by cross product, and also the cross. I mean, this is a curl, and also we define cross product. The cross product also involves epsilon. So there are many situations that involve the epsilon. So if we write physical law involving the epsilon, we better make sure that this one has the proper transformation property. Otherwise, the physical law will change according to the transformation. So that is not good. So that is. Doesn't have to be what? Doesn't have to be what?
90 degrees probably.
Doesn't have to be Cartesian. No, this is Cartesian. This is definition of a Cartesian. This is by using Cartesian coordinate. If not Cartesian coordinate, it's not like that. Okay, this doesn't like a spherical coordinate or whatever cylindrical coordinate. You cannot use that. It's okay. You make sure that you get the correct concept. This is only for Cartesian coordinate. Like if you want to write the curl or the curl operator in cylindrical coordinate or spherical coordinate, you need to do some more math to show that. And their formula, of course, get already derived from you. In fact, that we might be working on generalized coordinate system a little bit, right? But remember that that this is for Cartesian coordinate. Right. And all right, so once we have that, the next one is another example of using the epsilon is to define a sort of dual tensor, right? Okay, so all these are done. So if you have a second rank tensor that is anti-symmetric, you can define a dual vector, right? The definition is the C I is defined as 1/2 of this epsilon ijk C J. Okay, it means sum. They are contraction in J and K. So after all the sum, you only have the index I, the subscript I in the vector C. Okay, and this is anti-symmetric. In three-dimensional space, the C matrix Cij, J. It's just a 3x3 matrix, but because it's anti-symmetric, obviously anti-symmetric has a 0 element in the diagonal line, and this is C 1, 2. This is C1, 3. By the requirement that is anti-symmetric, this element is minus C1, 2. This element is minus C1, 3. This is C2, 3. This is minus C2, 3. So altogether, a 3x3 matrix only have 3 independent elements, because this one is the opposite of this one, so only have 3 of them, and the diagonal lines are 0. So only has 3 components, and therefore if we use this rule, you can check that the CI, say if C1, CI is, let me see, C1, 2, C1 is, I is 1, right? And then you sum over J and K. So there are only two cases that you need to consider. Because it's 1, you only have 2, 3, 1, 2, 3. Then you pick up the 2, 3 element, which is this one, right? That is positive, 1, 2, 3 is positive. Or 1, 3, 2, you pick up the 3, 2 element, which is this one. But the epsilon 1, 3, 2 is negative 1, but you have also a negative 1. So you add this 2, but you divide it by 2. This is 3, 2, 3. Right? It's okay. You can follow how you sum all of this. Right? And then the same consideration, you have 2, right? 2, there are two cases, so either 2, 1, 3 or 2, 3, 1. Now you need to determine what the value of epsilon 2, 1, 3 and 2, 3, 1, the two cases, right? And it's determined by how many permutation from 1, 2, 3. From 1, 2, 3, how many permutation you need to get to 2, 3, 1? This is first one, right? So this is negative, and obviously this one involving 2 permutations, so this is positive. So for the 2, this element, you have 1, 3. 1, 3 is this one. This is negative, right? 2, 1, 3 is negative. And 2, 3, 1 is this element. Okay, so negative, and this is negative. And that one is positive, so over negative, so negative. 2, 3, 1, 3. Right? And now this, the final one, 3. The two cases, 2, 3, 1, 2, or 3, 2, 1. Now how you get from here to this, you interchange 1 and 2, you get the 1 in here, and then you interchange 1 and 3. So 3. So this is positive, this is negative. Right? So 3, 1, 2, 1, 2 is this one. It's positive. 2, 1 is this one, is negative. So this is negative, so this is C1. Okay, with that. Right. But what the textbook didn't get this one. This is, oh, okay. The textbook ID is 3, 2, 1. This is 2, 3, 1, 2, and this is 3, 1. So your textbook defined it a little bit differently. This should call this 3, 1. That's negative 1, negative 3, 1. And this is 3, 1. Okay, that we recover the textbook. All right, so okay.
That's 0, 1, 2, 1, 3.
I don't get your question. Say that again.
Like
Yeah.
1.
Yeah, this 1, 3, but because anti-symmetric, you define this as C2, this is C31 element. This is anti-symmetric because negative C31. So originally I write C12 in here, C13 in here, but this is just to confirm the textbook is the textbook want to write it in these 3 elements. C2, 3, C31, C1, C2, to make it all positive sign. If I write C1, 3, that is negative. Okay, that is how we do all these consideration. All right, and all right, that is another example how you use this epsilon to define what we call this dual tensor. And in this case, it's a dual vector. It's from a tensor to a vector. Okay, and you know, I mean, at this level, it looks like it's just abstract, abstract application, but whatever there are applications involving physical law using this dual tensor. But leave it like that. The final example is a pseudoscalar. Right? If you have three vector, you have three vector A superscript I, B superscript J, C superscript K. You have three vector, or this three countervariant vector. Right, and then we define a quantity by summing over this by multiplying this equal ijk, right? And we define this as volume V. I mean, we'll see that there's a volume, but it's just a symbol here. But because we subcontracting all the indices, so there's no index left. So this is a quantity with the index, and supposedly everything's a tensor and vector. This is pseudotensor. This is all these are vector. When you do all the contraction, this you get a pseudoscalar, because according to the quotient rule, these transform like a contravariant vector. This transform like a pseudotensor, third rank pseudotensor. Whatever is left is just the just the determinant of S here, because this transform with a determinant S, and all the other transformation matrix will cancel out, right? And so the only thing change if you change it in a coordinate system with inversion or refraction, then that will change sign. Okay, so then you convince yourself that this one is just determinant of that correctly is A, B, C. It didn't matter whether put it in column or row. Right, A, B, C, A, T, B, C, D, B, C, D. You like you can do a transpose and change this to A, B, and C. It doesn't matter because determinant is the same, right? And you check that it's the same as this one, because this involve all the summation that the IJK are different. So it's that is exactly the same as what we define as a determinant that we just talked about. So we involve I1, 2, 3, then this one. This is 1, this is 2, this is 3, which is this, right? That is positive 1, and all the other check out. But this object is exactly this one, so it's determinant. So this determinant, you put three vector in either row or column. That is a pseudotensor, a pseudoscalar. Right? So that is an example of pseudoscalar, and in vector form, you can also write it according to what we just talked about. This is also A bar. And the usual vector notation is A bar. Right? And then you can use that to convince yourself this is a cross product, because whenever you have so this is like you have three vector A and B. They are not necessarily orthogonal, B and C, right? So, and the B cos C has direction normal, so it's hard to represent in the blackboard for three-dimensional space. But this is like you have this A and B. When you multiply together, it has a direction perpendicular to B and C, right? And then it depends on the theta. And added so B cos C is B C sine theta, right? And so, and then it has that direction perpendicular, whatever we call that. Hard to say. You need absolute value of B or C. has this element. So, and now you can do a dot product between this vector. This is B plus C. Okay? Do a dot product of this and that, right? And then it's like a projection of this vector on to this space, right? And if you write the parallelogram, it's hard to actually draw it. This is the volume. This is the volume of this parallelogram in three-dimensional space. And after you take into all this sign and whatever this theta is, right? And because the dot product involves the cosine of this alpha, and you can convince yourself that this is the volume. All right, so therefore this is what we call the V. It's okay. So that's just the final example. Okay, I thought I could go to 4.3 and start the general coordinate. The main idea of this chapter is in 4.3 that we want to generalize all these Cartesian coordinates. It's just give you the notation that you make it easier for you to generalize to tensor and to I mean general coordinate system. Yeah, this is a definition. Yeah, you can check that this is A dot B plus C. ABC is a vector. It is ABC vector, right? Because if you write because the I component, just according to what we have, is epsilon I J K B K. I object the I component is J C K. That is how you calculate the cross product in component form, right? And then you do a dot product. So basically A dot, this one meaning is sum over I, right? Sum over I. Then this one is just this one. Okay.